Hello, Stormy. Ignore dog. I'm going to turn it off. Okay. This is a recording of lesson 3-1 on page 110 of your Algebra 2 book. This is solving systems of linear equations by graphing. When we talk about systems of equations, we're talking about more than one. And in this section, you will only see two at a time. Thank goodness, right? Two systems of equations at a time. A solution to a system of equations can happen in one of two ways. Each equation will make a line when you graph it, and where they intersect is the solution point. So where at the point where both lines cross is the solution to your equation. It is an ordered pair, x comma y. So take a look at the paragraph that starts with graph systems of equations. It says a system of equations is two or more equations with the same variable. To solve a system of equations, find the ordered pair that satisfies all the equations. One way to do this is to graph the equations on the same coordinate plane. The point of intersection represents the solution. So they do this for us in example 1, where it says solve by graphing. Solve the system of linear equations by graphing. The two equations are 2x plus y equals 5 and x minus y equals 1. So if you were doing this on your own, you would graph both lines one at a time. You can do that by putting them in y-intercept form, which is y equals mx plus b, or you can, as the book does, the book does put them in y-intercept form. So for instance, 2x plus y equals 5. To put it into y-intercept form, we have to move the 2x to the other side by subtracting 2x from both sides. So the equation then becomes y equals negative 2x plus 5. So once you've got that first equation, graph it. You start at the y-intercept in the equation y equals negative 2x plus 5. The y-intercept is 5. And you would put a point at 0, 5. And you would use your slope, and in this case it's negative 2. So you would go down 2 to the right 1, put a point, down 2 and to the right 1, and put a point. Generally, you want to put about 4 or 5 points so that your rubber band makes a nice line for you. And once you have the first line, you graph the second line. The second equation was x minus y equals 1. Well, to get that in y-intercept form, we need to move the x to the other side first by subtracting it from both sides. So we get negative y equals negative x plus 1. But we have a negative y, so we have to divide both sides by negative 1 and get y equals plus x minus 1. So again, to start graphing this, you put your first point on the y-axis at negative 1, because negative 1 is your y-intercept. Then you use your slope 1. Slope again is rise over 1, so it's 1 over 1. Starting from negative 1, 0, you go up 1 and to the right 1, up 1 and to the right 1. And do that for 3 or 4 points. You can also go down 1 and left 1, starting at the y-intercept. So take a look at your tactographic page. It should be the next thermoform page. The book shows it, both lines graphed for you, and they label it. There's one with positive slope and one with negative slope. The one with positive slope is our line x minus y equals 1. Now when you do this, it's okay. you can write your equation in y-intercept form on your graph or on your paper. I will accept that. And the other line is 2x plus y, negative 2x plus y equals 5. So look for the point where they intersect. And they labeled it for you. The lines intersect at 2, 1. They intersect at 2 points over on the x-axis and 1 point above the on the y-axis. That is the solution to your equation. And you can always check. Below the example, there's a section for checking. You plug in the point to each equation and see if it works out. So you plug in 2 for x and 1 for y and see what you get. So in the first equation was 2x plus y equals 5. You plug in 2 for x and 1 for y. You get 2 times 2 is 4 plus 1 is 5. And then on the other side it says equals 5. So hooray, it works for the first equation. Now when we plug in 2 for x and 1 for y in the second equation is x minus y equals 1. Then we get 2 minus 1, which is also 1, equals 1. Check. So therefore our solution is the ordered pair 2, 1. At the top of the next page, after the page break in Braille, we have a break-even point example. This I am not concerned about. We can skip it for now. All I want you to know about example 2 is a break-even point occurs in business, where if you were to go to Starbucks, I'm not sure if you like coffee, but if you go to Starbucks and you buy a cup of coffee, it's like $3.95 in Oregon for a mocha, right? And each of those things costs money. The roof over the employees' heads costs money. The employees themselves cost money. The paper cup it comes in costs money. The milk costs money. The chocolate costs money. And the coffee costs money. So the break-even point is where, when you buy all the stuff for your business, where does that equal the same amount people are paying you for your product? So how many cups of coffee does it take to break even with the rent, the employees, and the stock, right? And you wouldn't make a profit if you made less than the break-even point. And you start making a profit when you pass the point where you break even. That makes sense. Okay, let's move on to the paragraph where it says classifying linear equations, or classifying systems of equations. It says graphs are systems of linear equations may be intersecting lines, parallel lines, or the same line. A system of equations is consistent if it has at least one solution, and it is inconsistent if it has no solutions. Okay, so the only time a set of systems of equations is inconsistent is if it does not have a solution. Well, when might an equation not have a solution? If two lines must touch. Well, when two lines are parallel, they never intersect, do they? So lines that are parallel do not have a solution and therefore would be considered inconsistent. We also can have two other kinds of situations that are consistent. The one we saw in example 1, where only one solution was apparent, that was when both lines crossed at a single point. That is called consistent independent. And the way I remember that is, okay, it's consistent, it has a solution, and it's independent because there's only one. It's independently alone. Independent consistent solution is when there's only one solution. A consistent dependent solution occurs when you you graph two lines and they share every single point. And we'll see that in the examples. So let's take a look at example 3, intersecting lines. All right, I think we're going to see it in this example. So graph the system of equations and describe it as is it consistent or inconsistent, consistent and dependent, or inconsistent, pardon me, let me re-say that. Describe it as consistent and independent, consistent and dependent, or is it inconsistent? And I encourage you to write down these definitions in your notes. So the two equations are x plus 1/2 y equals 5, 3y minus 2x equals 6. So again, the first step you always do in these equations is write them in slope-intercept form. That is, put y all by itself on the left equals to everything else. Y equals something x plus something. So to do that in the first equation, we have x plus 1/2 y equals 5. Well, we have to subtract x from both sides, and that gives us 1/2 y equals negative x plus 5. To get rid of 1/2, we have to multiply by 2. So we have y equals negative 2x plus 10. So again, graph that first before moving on to the next equation. Give it a graph. So start at the y-intercept. In this case, the y-intercept is 10 because it was negative 2x plus 10. So we put a point at 0, 10. And our slope is negative 2 over 1. So that's down 2. So start at 0, 10, and go down 2 points and over 1. Down 2 points and over 1. And put your point every time you do that. Do that again so you have a nice straight line with your rubber band. And once that is done, we can move on to the next equation. Next equation is 3y minus 2x equals 6. Well, again, put it in y-intercept form, which is where we get y all by itself on the left and move everything else over to the right side. So first, we got to add 2x to both sides because it's a negative 2x. So then we get 3y equals 2x plus 6. Then to get rid of a multiply by y, we have to divide by 3. Well, y equals 2/3 x plus 2. Okay, 2/3 x plus 2. Well, what is our y-intercept? Our y-intercept in this equation is 2. Therefore, our first point starts at 0, 2. We start there, and our slope is 2 over 3. Rise over run. So 2 over 3 means go up 2 spaces and right 3 spaces. Put a point. Up 2 spaces from there and right 3 spaces. Do that until you have a nice straight line with your rubber band and see where they intersect. So take a look at how the book did it on the next thermoform page. The positive slope line and negative slope line are here. 3y minus 2x plus 6 is the positive slope line, so that's the one going uphill. And x plus 1/2 y equals 5 is the negative slope line, as you remember, because we had a slope of negative 2 in that line. So find the point where they intersect and find out what point that is by starting at the origin and counting. How many points over and how many points up is that spot where they intersect? Well, they go over 3 on the x-axis and they go up 4 on the y-axis. So therefore, our point is 3, 4. And again, if you're not sure, plug them into the equations and see if 3, 4 is a solution. Let's check out example 4. It says same line. So as you can imagine, same line probably means they're the same line when they graph it, right? That means they're going to be on top of each other, the two lines. Let's see what that looks like. It says graph. Oh, hold on. Before we move on, what kind of solution is this? Is it consistent or inconsistent? It is consistent because it actually does have a solution. Is it dependent or independent? Well, there's only one solution, so it's on its own, so it's independent. Therefore, the solution is consistent and independent. Sorry about that. Now let's move on again to example 4. It's right below in the print page, so it shouldn't be too far down the Braille page. Graph the system of equations and describe it as inconsistent or consistent dependent or consistent independent. Our two equations are 9x minus 6y equals 24 and 6x minus 4y equals 16. Okay, again, start off the same way. Solve for y, and put it into y-intercept form. And you do that by moving the x over to the other side. So the first equation becomes y equals 3/2 x minus 4. And the second equation, we have to move x over and then divide by -4. So the second equation becomes y equals 3/2 x minus 4. They're the same exact equations, aren't they? The first equation we got when we put it in y-intercept form was 3/2 x minus 4. And the second equation when we put it into y-intercept form was also 3/2 x minus 4. So take a look at the thermoform page, and as you can see, there's only one line. One line. So both lines are the same. That is, each equation forms the same line. So therefore, all the points, they share all of the points. What you plug in to the first equation, 9x minus 6y equals 24, you will also get the same answer when you plug it into 6x minus 4y equals 16. So when you graph two lines and they happen to be the same exact line, this is called a system of equations with infinitely many solutions. They share all points. And in mathematical language, we call this a consistent and dependent solution. Consistent and dependent because they share all points. Okay, very good. Let's turn the page. And we are going to look at one last example. It's at the very top. It should be right after the page break. Parallel lines. So it says, graph the system of equations and describe it as consistent dependent, consistent independent, or inconsistent. All right, our two equations are 3x plus 4y equals 12 and 6x plus 8y equals -16. So again, start off with your first equation. And in this case, it's 3x plus 4y equals 12, and put it into y-intercept form. That is, get y all by itself. To do that, we got to move the 3x over to the other side, and then divide the whole darn thing by 4. And the book says that is -3/4 x plus 3. Okay, great. And then we do it for the second equation. 6x plus 8y equals -16. Well, to get the y by itself, we have to subtract 6x from both sides and divide by 8 to get rid of the 8 multiply y. And the book says that is y equals -3/4 x minus 2. Okay, take a look at both equations that they found. -3/4 x plus 3 and -3/4 x minus 2. What do you notice? They both have the same slope. What did we learn last chapter about lines that have both the same slope? They are parallel. Take a look at the thermoform page that shows you what this looks like. You have 6x plus 8y equals -16 as the bottom line, and the top line is the equation 3x plus 4y equals 12. As you can see, they are parallel. And what do we know about parallel lines? They never intersect. Therefore, they will never ever have a solution. So this is known as a no-solution system of equations. And we call that inconsistent because it will never have a solution. Okay, the last thing I want to do today is talk about the concept summary box. right below the little paragraph that says, the relationships between the graph of a system of equations and the number of solutions is summarized below. Okay, take a look. The first one, the first thermoform page, says consistent and independent. So they just give you a generic graph. You have your x and y axis and two lines. It looks like an X in print. So a consistent and independent solution has one solution. Just one. They cross at one point. And therefore, it's an independent solution because it's all on its own. So consistent and independent. The next type of solution is consistent and dependent. Consistent and dependent. This is where, when you graph both lines, they're the exact same line. So it kind of looks like you only have one line, right? On the thermoform page, they only it looks like they just drew a really simple line straight through the origin. Or almost through the origin, anyway. That's one line. That means the two lines share every single point. And because they share every single point, there's infinitely many solutions. This is called consistent and dependent. It's dependent because there's many. They all depend on one another, all these solutions. Okay, let's look at the final thermoform page and inconsistent solutions. That's like what we just saw in the last example. The only time you're ever going to get inconsistent solutions is if your lines are parallel. And as you can see, they both have a negative slope, and they're never ever going to cross each other. So it's inconsistent. These are inconsistent solutions. All right. I hope that this helps you, Stormy. I am going to say that I am very sorry to hear that you've been so sick, and I really hope you're feeling better. Okay? So go ahead and try and do 4, 5, and 6 on this page. I want you just to do 4, 5, and 6 for me. Okay? So please let me know if you want to set up an appointment with me to work on this stuff. I am more than happy to find some time after school to do so. So please feel better. And I will send this to you right now. Have a